Somewhere within Einstein's work, there is a quiet idea, one that suggests reality itself may not be what it appears to be. Not the famous bending of space, not the slowing of time near massive stars, but something far more unsettling. A possibility that what we call reality is not fixed, not continuous, and perhaps not even the same for everyone experiencing it. Tonight, we're not following the well-known paths of relativity. Instead, we're stepping into the quieter corners of Einstein's thinking, the hidden ideas that were often overlooked, misunderstood, or simply too strange to fully accept. Because scattered across his work are clues. Clues that light is not truly a wave, that time does not flow the same for all observers, that space itself can twist, stretch, and even connect distant regions in ways that defy intuition. And if you've ever watched our Velorin episode on the illusion of time, you might remember that unsettling feeling, the sense that what we experience as now could be something far less solid than it seems. Tonight, we go deeper. We follow the threads Einstein left behind, ideas that quietly reshaped physics, but also opened questions that remain unresolved even today. Because when you place them side by side, these ideas begin to form a pattern that suggests reality is not a single stable stage, but something far more fluid, layered, and mysterious. So as the universe slowly settles around you, take a moment to get comfortable. And if you enjoy exploring these quiet cosmic mysteries, consider subscribing, liking the video, and turning on the bell so you don't miss future journeys. You can also join as a member if you'd like to support the channel, and let me know in the comments where you're listening from tonight. Now, let's begin. At first, the mystery seems small, almost trivial. A simple observation involving light and metal. Shine light onto a clean surface and sometimes electrons are released. A faint electric current appears, as if the light itself is knocking tiny particles loose. For years, scientists believed they understood what was happening. Light was a wave, a smooth and continuous flow of energy, spreading out through space like ripples across water. And if that were true, then the explanation should have been simple. Brighter light, more energy. More energy, faster electrons. Felt obvious, almost too obvious. But reality, as Einstein would later suggest, does not always follow what feels obvious. When experiments became more precise, something strange began to emerge. The brightness of the light did not determine how energetic the electrons were. Instead, it was the color of the light, its frequency. A dim beam of ultraviolet light could instantly eject electrons with high energy, while an intense red light, no matter how bright, could fail completely, producing nothing at all. It was as if the universe was ignoring intensity and paying attention only to something deeper, something hidden within the nature of light itself. This was the first quiet fracture in what people believed reality to be. Because if light were truly a wave, then energy should accumulate gradually. A weak light should still work, given enough time. The electrons should absorb energy slowly, like filling a cup drop by drop, until finally they had enough to escape. But that did not happen. The electrons either left instantly or not at all. There was no waiting, no gradual build-up, no smooth transition. It was sudden, discrete, almost as if energy arrived in tiny, indivisible packets. And this is where Einstein made a leap that changed everything. He proposed something deeply unsettling for the time. What if light was not just a wave, but also made of tiny particles? Not continuous, but granular. Each particle carrying a specific amount of energy, determined not by brightness, but by frequency. In this view, light was no longer a smooth flow, but a stream of individual quanta later called photons. Each photon like a tiny messenger, delivering a fixed amount of energy in a single interaction. Now the mystery began to make sense. If a photon did not carry enough energy, no electron would be released. No matter how many photons arrived, no matter how bright the light became, if each individual packet was too weak, nothing would happen. But if even a single photon carried enough energy, it could instantly eject an electron without delay. Suddenly, the strange experimental results were no longer strange at all. They were inevitable, but with that explanation came something far more profound. Reality itself was no longer continuous. Energy, once thought to flow smoothly, was now arriving in discrete steps. Not a river, but a rain of individual droplets. And this idea did not stay confined to light. Spread, quietly at first, then with increasing force. If light could behave like particles, what about matter? What about the very fabric of reality? This was the beginning of a deeper transformation. A shift away from the comforting idea that the universe is smooth and predictable, towards something more fragmented, more uncertain, and perhaps more unsettling. Because if energy comes in discrete packets, then interactions are not continuous processes, but events. Moments where something either happens or does not. There is no in-between, no gradual transition, just thresholds, invisible boundaries that must be crossed. You can almost feel it beneath the surface of everyday experience, even if it remains hidden. The idea that change does not always happen slowly, that sometimes nothing happens until suddenly everything does. Einstein's hidden idea here was not just about light. It was about how reality itself might be structured, not as a smooth continuum, but as something built from indivisible pieces, interacting in ways that only appear continuous from a distance. And this raises a quiet question, one we will return to again and again. If reality is made of these discrete moments, these tiny packets of interaction, then what we perceive as a continuous world, is it truly continuous at all? Or is it simply an illusion, emerging from something far more fragmented beneath the surface? As we move forward, this question will begin to connect with others, with time, with space, with the very idea of what is real, because this was only the first crack. And once a crack appears in reality, it rarely stays small. If light could behave like particles, then a deeper question quietly emerged. What if particles could behave like waves? At first, this idea felt almost absurd. Matter, after all, seems solid, definite, anchored in place. A rock does not spread out like a ripple. An electron, small as it may be, was still imagined as a tiny object moving along a path, like a miniature planet orbiting a nucleus. Predictable, traceable, real in the classical sense. But as experiments grew more refined, something unexpected began to reveal itself. Electrons, when passed through certain experimental setups, did not behave like tiny solid objects. Instead, they created patterns, delicate, repeating bands of light and dark, the kind only waves could produce. Interference patterns, the unmistakable signature of something spreading out, overlapping with itself, and recombining. This was not supposed to happen, because for a particle to create an interference pattern, it would need to pass through multiple paths at once. Not one trajectory, but many. Not a single location, but a spread of possibilities. It suggested that, at a fundamental level, matter was not confined to a single point until something forced it to be. And this is where reality began to soften. Imagine releasing a single electron toward a barrier with two narrow openings. If it were a particle in the classical sense, it should pass through one opening or the other, leaving a simple pattern behind. But that is not what happens. Even when electrons are sent one at a time, something remarkable emerges over time. A pattern builds, one that can only be explained if each electron somehow explores both paths simultaneously. Not physically splitting, but existing in a kind of distributed state. A wave of possibility. Only when the electron is observed, when it interacts in a way that forces a definite outcome, does it appear in one place. A single point, a single event, as if the wave suddenly collapses into a particle. And in that quiet transition, something profound is revealed. Before observation, the electron is not in one place or another. It is described by a range of possibilities, a cloud of potential outcomes. Reality at this level is not a fixed thing waiting to be discovered, but something that only becomes definite when interaction occurs. This idea is often described carefully, cautiously, with precise language. But beneath that careful explanation lies something deeply unsettling, because it suggests that reality does not fully exist in a definite form until it is observed. Not observed by a conscious mind necessarily, but observed in the sense of interaction, measurement, contact, a moment where possibility becomes fact. And this raises a question that quietly echoes through all of physics. What is the nature of something before it is observed? Is it real in the way we understand reality? Or is it something else? Something that only becomes real when it is forced to choose? Einstein himself was deeply uncomfortable with this implication. The idea that nature operates on probabilities rather than certainties, that outcomes are not determined until measured, felt incomplete to him. He believed there must be a deeper layer, hidden beneath the probabilities, restoring order and determinism. But as experiments continued again and again, they pointed in the same direction. The probabilistic nature of reality was not a flaw in our understanding. It was a feature of the universe itself. And so the second crack widened. First, energy was no longer continuous. Now, matter itself was no longer definite. The solid world we experience built from atoms and particles, seemed to rest on a foundation that was anything but solid. Instead, it resembled something fluid, a shifting landscape of probabilities, where objects do not have exact positions or paths until those properties are brought into focus through interaction. And yet, at larger scales, everything appears stable, solid, predictable. The randomness averages out. The probabilities settle into patterns we can rely on. The world feels continuous, even if it is not. This creates a kind of illusion, a smooth surface hiding a deeply granular and uncertain structure beneath, like looking at the ocean from far away, calm, continuous, unbroken, but up close, it is made of countless individual waves, constantly shifting, never truly still. Einstein's hidden ideas begin to converge here. The photoelectric effect showed that energy arrives in discrete packets. Wave-particle duality showed that matter itself exists in a state of uncertainty until observed. Together, they suggest that reality is not what it appears to be on the surface. It is not continuous. It is not fully deterministic. It is not entirely independent of observation. And this leads us gently toward the next question, one that touches something even more familiar: time. Because if matter and energy behave in ways that defy our intuition, what about time itself? Is it as stable as it feels? Or is it too part of the illusion? Time feels simple. It flows forward. It moves the same for everyone. A shared rhythm, ticking quietly in the background of existence. When we say something happened now, we assume that now means the same thing everywhere, that the universe shares a single present moment, a universal clock that keeps everything in sync. But Einstein's hidden ideas suggest something far more unsettling. What if there is no universal now? To begin understanding this, imagine something simple: two flashes of light occurring at different places. From one perspective, they happen at exactly the same time, perfectly synchronized. But from another perspective, moving relative to the first, those same two events no longer appear simultaneous. One happens before the other. At first, this sounds like a trick of perception, a delay in receiving signals. But it is not. Even after accounting for how long light takes to travel, even after correcting for distance and measurement, the disagreement remains. It is built into the structure of reality itself. This is what Einstein revealed: simultaneity, the idea that two events happen at the same time, is not absolute. It depends on how you are moving, and this changes everything. Because if different observers cannot agree on what happens at the same time, then the idea of a single shared present begins to dissolve. There is no universal slice of reality called now that applies everywhere. Instead, each observer carries their own version of the present, shaped by their motion through space. It is a quiet shift, but a profound one. Imagine drifting through space, watching distant stars explode. From your perspective, two explosions might appear perfectly synchronized. But another observer, moving differently, would see one explosion happen first, and the other later. Both observations are equally valid. Neither is more correct than the other. Reality, in this sense, is no longer a single fixed timeline. It becomes something more flexible, a structure where time and space are woven together, and where different observers carve that structure into different slices. This idea is difficult to feel because in everyday life, the effect is too small to notice. Our speeds are slow compared to light. Our experiences are local. The differences blur into insignificance. And so we grow up believing that time is universal. Because for us, it almost is. But at higher speeds, near the speed of light, the illusion breaks. Observers moving differently begin to disagree not just about when things happen, but about the order in which they happen. Events that seem simultaneous in one frame become separated in another. The structure of time tilts like a surface viewed from different angles. And here is where the deeper implication begins to emerge. If there is no universal present, then what does it mean for something to exist right now? The idea of a shared moment across the universe becomes meaningless. Instead, reality becomes a kind of four-dimensional landscape where past, present, and future all exist together, and what we call now is simply the particular slice we happen to experience. A perspective, not a universal truth. This is sometimes described as the idea of a block universe, though the name is less important than the feeling it evokes. The sense that time does not flow in the way we perceive it, but is instead laid out like a vast structure where different observers trace different paths. And if that is true, then the present moment, the one you are experiencing right now, is not something uniquely unfolding. It is simply where you are along your path. Feels immediate, alive, but in the deeper structure of reality, it may already exist alongside all other moments. Einstein himself once hinted at this perspective, suggesting that the distinction between past, present, and future might be more of an illusion, persistent, but not fundamental. And when you place this idea next to the others we've explored, a pattern begins to form. Energy is not continuous, comes in discrete packets. Matter is not definite. It exists in probabilities until observed. And now, time is not universal. It depends on motion, on perspective. Each of these ideas alone is enough to unsettle our intuition. But together, they begin to reshape something deeper. They suggest that reality is not a fixed stage where events unfold in a single shared order. Instead, it is something more fluid, more relational, something that depends on how it is observed, and from where. And this brings us to a quiet but unavoidable question. If time itself depends on perspective, if there is no single universal now, then what anchors reality at all? What keeps it from dissolving entirely into relative viewpoints? As we move forward, we will begin to explore how gravity itself enters this picture. Not as a force pulling things together, but as something that reshapes time and light, bending reality in ways that are both subtle and profound. Because the deeper we go, the more it begins to feel like reality is not something we stand inside, but something we are moving through in ways we are only beginning to understand. By now, a quiet pattern has begun to emerge. Light is not simply a wave. Matter is not fully defined. Time is not universal. Each idea alone is strange, but together they begin to shift something deeper. They suggest that reality is not fixed in the way we once believed, that it does not exist as a single, objective structure waiting to be observed the same way by everyone. Instead, it seems to depend on perspective. And this is where Einstein's hidden ideas become even more unsettling. Because once simultaneity breaks, once there is no universal now, something else begins to fade as well. The idea of a single, shared reality. Imagine two observers moving differently through space, not just standing in different places, but moving at different speeds. Each carries their own clock, their own measurement of time, their own slicing of the universe into past, present, and future. And because of this, they do not just disagree about when things happen. They disagree about reality itself. Events that are simultaneous for one observer are not simultaneous for another. Events that appear connected in one frame may appear separated in another. Even the sequence of events, what happens first and what happens later, can depend on motion. This is not a matter of confusion or misinterpretation. It is not because one observer is mistaken. Both are correct. Reality, in this sense, is not absolute. It is relational. It depends on how you move through space and time. This idea quietly dissolves something we often take for granted: the belief that there is a single, objective version of events unfolding across the universe. Instead, what emerges is a kind of layered reality, where different observers experience different but equally valid versions of how events are arranged. And yet, this does not lead to chaos. There are still rules. There are still structures that hold everything together. For events that can influence each other, events connected by signals that travel at or below the speed of light, all observers agree on their order. Cause still comes before effect. The universe preserves its deeper consistency. But beyond that, in regions where events are too far apart to affect one another, the order becomes flexible, not fixed, not universal. And here, something subtle begins to take shape. Reality is not just what happens. It is also how it is connected. The structure of space-time determines what can influence what. And within that structure, different observers trace different paths, constructing different narratives of events, all consistent within their own frame. This is not unlike looking at a vast landscape from different angles. From one position, two distant mountains may appear aligned. From another, they separate. Neither view is wrong. Each is shaped by perspective. But in the case of reality, the landscape itself includes time. And so perspective does not just change how things look. It changes how events are ordered. This leads to a deeper, almost philosophical question. If reality depends on perspective, then what does it mean for something to truly happen? Is there a single version of events, or many overlapping versions, each tied to a different observer? Einstein's work does not give a simple answer. Instead, it offers a framework where multiple perspectives coexist, each internally consistent, each describing the same underlying structure in different ways. It is a kind of harmony, but not the simple harmony we once imagined. More like a complex piece of music, where different listeners focus on different melodies, different rhythms, yet all are part of the same composition. And as we begin to see this, another connection starts to form. The probabilistic nature of matter, the discrete nature of energy, the relativity of time, all point toward a reality that is not built from fixed, absolute pieces, but from relationships, interactions, perspectives. Reality becomes something that is not simply there, but something that emerges through the interplay between observer and system. And this brings us gently toward the next layer. Because if perspective shapes time, what about gravity? What about massive objects, stars, planets, black holes? Do they also shape reality in ways that go beyond simple motion? The answer, as Einstein would later reveal, is yes. Gravity does not just pull objects together. It reshapes the very structure of space-time itself. It changes how time flows. It changes how light behaves. It alters the energy carried by photons, stretching and shifting them as they move through curved regions of the universe. And in doing so, it adds another layer to this unfolding mystery, because now, reality does not only depend on how you move, it also depends on where you are, and how deep you are within the invisible curves of space-time. As we continue, we will begin to explore how gravity quietly alters the fabric of existence, changing not just motion, but the very rhythm of time and the color of light itself. Because the deeper we look, the more it begins to feel like reality is not a fixed stage at all, but something far more dynamic, something shaped by motion, by position, and perhaps by observation itself. By now, something subtle has shifted, not in the equations, not in the experiments, but in the way reality itself begins to feel. Light is no longer continuous. Matter is no longer certain. Time is no longer universal. And reality itself no longer absolute. Each idea has gently loosened a thread that once held our understanding together. And now, as those threads begin to separate, a deeper question quietly emerges beneath them all. If reality depends on perspective, then what is truly real? At first, this question seems abstract, philosophical, something distant from physics. But in truth, it sits at the very center of everything we've explored so far. Because each of Einstein's hidden ideas has pointed toward the same direction. Not directly, not loudly, but persistently. That what we experience is not the full picture. Take light, for example. What appears to us as a smooth beam is, at a deeper level, a stream of individual packets. Take matter. What feels solid and continuous is built from probabilities, from distributions that only become definite when observed. Take time. What feels like a shared, universal flow is actually fragmented, dependent on motion, different for every observer. And yet, despite all of this, our experience remains stable. The world feels continuous, solid, ordered. This creates a kind of tension between what reality appears to be and what it seems to be underneath. It is almost as if we are living on the surface of something deeper, something more complex, a layer where the strange behaviors of the universe average out into something familiar, something predictable, something we can navigate without ever noticing the deeper structure below. Like walking across frozen water, never seeing the currents moving beneath the ice. Einstein's hidden ideas begin to reveal those currents. They suggest that reality is not built from solid, unchanging pieces, but from interactions, from events, from relationships between energy, matter, space, and time, and perhaps most importantly, from perspective. Because every observation, every measurement, every experience is made from somewhere, from a particular position, moving at a particular speed, within a particular gravitational environment. There is no view from nowhere, and this means that what we call reality is always, in some sense, a version of reality, a slice, a perspective shaped by where and how we exist within the universe. But this does not make reality arbitrary. There is still structure, still consistency, still laws that hold everything together. Different observers may disagree on timing, on ordering, on certain measurements, but they all agree on the deeper relationships, the connections between events, the rules that govern how things can influence one another. Reality, then, is not a single fixed picture. It is more like a network, a web of relationships that remains consistent even as the perspectives within it shift. And this is where the quiet beauty of Einstein's thinking begins to emerge. He did not replace certainty with chaos. He replaced simplicity with depth. A universe that once seemed rigid and absolute becomes something more flexible, more subtle, but also more unified. A structure where space and time are intertwined, where energy and matter are connected, where observation and interaction play a fundamental role. And yet, for all this understanding, something remains unresolved. Because if reality depends on perspective, if what we see is always shaped by how we observe, then is there a deeper layer still hidden from us? A level of reality that exists independently of all perspectives. Einstein believed there was. He suspected that beneath the probabilistic nature of quantum mechanics, beneath the relativity of time, there must be a deeper order, a more complete description, something that restores a sense of continuity and determinism. But whether that deeper layer exists, or whether reality is fundamentally built on these strange, shifting principles, remains an open question. And it is this question that carries us forward. Because everything we have explored so far, the nature of light, the uncertainty of matter, the relativity of time, has been leading us toward something even more profound. Toward the idea that reality itself is shaped not just by motion, but by gravity, by the presence of mass, by the invisible curvature of space-time that bends not only the paths of objects, but the flow of time, and even the energy of light itself. In the next part, we will begin to explore this deeper layer, where gravity does not simply pull, but transforms, where light changes color as it climbs through space, where the universe itself expands, driven by a force Einstein once thought was a mistake, and where space may not be as separate as it appears, but quietly connected in ways that challenge everything we think we know. So as the ideas settle gently into place, and the surface of reality begins to feel just a little less solid, we continue. There is something comforting about light. It feels constant, reliable, a universal messenger moving through space at a fixed speed, untouched by the things that influence matter. Planets bend, objects fall, time stretches, but light, we often imagine, simply travels, pure and unaffected. But Einstein's deeper ideas reveal something far more subtle. Light is not immune to gravity, not because it is pulled like a falling object, but because gravity reshapes the stage through which light moves. And when that stage changes, so does the light. To begin to feel this, imagine a beam of light escaping from the surface of a massive object. A dense star, for example. From the perspective of the light itself, nothing unusual happens. It travels outward, always moving at the same speed, always carrying its energy forward. But to an observer far away, something has changed. The light arrives, slightly different. Its color has shifted. Not dramatically, not in a way the eye would notice immediately, but measurably. The light has been stretched. Its wavelength increased. Its frequency lowered. It has shifted toward the red end of the spectrum. This is known as gravitational redshift, and it carries a quiet but profound implication. Gravity does not just affect motion. It affects energy. To understand why, we need to return to something we touched on earlier, the relationship between time and gravity. In Einstein's view, gravity is not a force pulling things downward. It is a curvature of space-time, a distortion in the fabric that defines both space and time together. And in regions of stronger gravity, time itself runs more slowly. This is not a metaphor. It is not an illusion. Clocks placed deeper within a gravitational field tick more slowly compared to clocks farther away. Every process tied to time, every vibration, every oscillation, every cycle is affected. And light is no exception. Light can be thought of as a kind of rhythm, a wave defined by repeating peaks and troughs. The frequency of that rhythm determines its color. Higher frequency, bluer light. Lower frequency, redder light. So when light climbs out of a gravitational field, it is moving from a region where time flows more slowly to a region where time flows more quickly. And from the perspective of the distant observer, the rhythm of that light appears stretched, slowed, redshifted. It is not that the light itself has lost energy in the way an object loses energy through friction. It is that the framework in which that energy is measured has changed. Time itself has shifted, and so the light appears different. This idea is quiet, but it carries a deeper meaning, because it tells us that even something as fundamental as the energy of light is not absolute. It depends on where you are in the universe, on how deep you are within a gravitational field, on how space-time is curved around you. Reality, once again, reveals itself to be relational. But this is not just a theoretical idea. It has been measured, confirmed, and woven into the technologies we use every day. Even here on Earth, the effect exists, small but real. Clocks at higher altitudes tick slightly faster than clocks at lower altitudes. Signals sent from satellites must account for this difference, or errors would quickly accumulate. Positions would drift, systems would fail, and so, quietly, every time we navigate using satellites, we are correcting for the fact that time itself flows differently depending on gravity, that light carries the imprint of where it has been. But in more extreme environments, the effect becomes far more dramatic. Near a white dwarf star, light escaping its surface is noticeably redshifted. Near a neutron star, even more so, and near a black hole, the effect becomes so extreme that something extraordinary happens. Light emitted just outside the boundary of a black hole, the event horizon, becomes stretched to such an extent that, to a distant observer, it appears to slow, to fade, to freeze in time. The signal never quite disappears, but it becomes infinitely redshifted, slipping beyond detectability. From the outside, it is as if time itself has stopped at the edge. And this brings us back to something we felt earlier, the idea that time is not universal. Now we see that it is not only motion that changes time, but gravity as well. Where you are matters just as much as how you move. And so reality becomes even more layered. Different observers moving differently, at different positions in gravitational fields, each experience time in their own way. Each sees light differently. Each measures energy differently. And yet, all of these perspectives remain consistent within the deeper structure of space-time. This is the quiet elegance of Einstein's vision. Reality is not broken. It is flexible. It adapts, depending on perspective, position, and motion, but it remains coherent beneath it all. And still, questions remain, because if gravity can change time, and time can change how light is perceived, then what else might be shaped by this invisible curvature? What else might be quietly altered by the structure of space-time itself? As we move forward, we will encounter one of Einstein's most curious ideas, one he once considered a mistake. An addition to his equations that he later abandoned, only for it to return, decades later, as one of the most important discoveries in modern cosmology. A force that does not pull inward, but pushes outward, gently, silently, expanding the universe itself. There is something almost poetic about the idea that one of Einstein's most famous mistakes might actually describe the fate of the entire universe. At the time, it did not feel like a mistake at all. Einstein had completed his theory of general relativity, a framework that described gravity not as a force, but as the curvature of space-time. His equations were elegant, powerful, and flexible, capable of describing an entire universe. But when he applied them to the cosmos as a whole, something troubling appeared. The universe, according to his equations, could not remain still. Gravity, acting over vast distances, would pull everything inward. Galaxies would drift closer. Matter would collapse. The universe, left to itself, would either shrink or expand, but it could not remain static. And yet, in Einstein's time, the prevailing belief was that the universe was eternal and unchanging. a steady, balanced structure that had always existed as it was. This assumption felt natural, obvious. There was no clear evidence suggesting otherwise. So Einstein did something subtle but profound. He modified his own equations. He introduced a new term, something that acted like a gentle, repulsive influence, a kind of pressure built into space itself, pushing outward and counteracting gravity's inward pull. With just the right value, this addition could perfectly balance the universe, holding it in a delicate static equilibrium. This term became known as the cosmological constant. At first, it seemed like a clever solution, a way to reconcile theory with expectation. But nature, as it often does, had its own plans. In 1929, observations revealed something unexpected. Distant galaxies were not standing still. They were moving away, and not randomly but systematically. The farther away a galaxy was, the faster it appeared to be receding. The universe was expanding. This discovery changed everything. Suddenly, Einstein's modification was no longer needed. His original equations, without the cosmological constant, naturally predicted an expanding universe. The very thing he had tried to prevent was, in fact, real, and so he reportedly referred to the cosmological constant as his greatest blunder. But the story did not end there, because decades later, something even stranger was discovered. As astronomers studied the expansion more carefully, they expected to see it slowing down. Gravity, after all, should be pulling everything back together, gradually reducing the rate of expansion over time. But that is not what they found. Instead, the expansion was accelerating. The universe was not just growing, it was speeding up, and suddenly the cosmological constant returned. The same term Einstein had introduced, and then discarded, now offered the simplest explanation. A small positive value could act as a kind of built-in energy of empty space, pushing the universe outward faster and faster over time. Today, this effect is often called dark energy. It is estimated to make up the majority of the universe's total energy content, yet its true nature remains unknown. It does not emit light. It does not interact in familiar ways. It simply exists, quietly influencing the expansion of everything. And this brings us back to something deeply unsettling. Empty space is not empty. It has energy, structure, influence. Space itself is doing something. This idea reshapes our understanding of reality in a subtle but profound way, because it suggests that the vacuum, the seemingly empty backdrop of existence, is not passive. It is active, dynamic, capable of shaping the fate of the cosmos. And yet, there is a problem. When physicists attempt to calculate the energy of empty space using quantum theory, they arrive at a value that is wildly different from what we observe. Not just slightly off, but unimaginably larger. The discrepancy is so extreme that it is often described as the worst prediction in all of physics. This means that something is missing. Some deeper understanding of how quantum mechanics and gravity fit together, something that has not yet been fully revealed. Einstein's mistake, then, becomes something more than a historical curiosity. it becomes a clue, a hint that even within our most successful theories, there are gaps, places where our understanding is incomplete, where reality behaves in ways we cannot yet fully explain. And this connects back to the pattern we have been following. Reality is not as simple as it appears. Energy is quantized. Matter is uncertain. Time is relative. And now, even empty space carries hidden properties that shape the universe on the largest scales. What once seemed like a stable, unchanging backdrop becomes something alive with subtle influence. And this raises another quiet question. If space itself can expand, if it carries energy, if it shapes the fate of everything within it, then what exactly is space? Is it just a stage where events unfold? Or is it something more fundamental, something with its own structure, its own dynamics, its own role in the unfolding of reality? As we move forward, this question will take us somewhere even more unexpected. Because Einstein's equations do not just allow space to expand. They also allow something far stranger. They allow space to connect, to form bridges between distant regions, to create shortcuts not through space, but through space-time itself. And in exploring those possibilities, we begin to touch on one of the most intriguing ideas Einstein ever helped uncover, something that would later be known as a wormhole, a connection that exists but may never be crossed. There is a quiet moment in Einstein's work where the equations seem to whisper something unexpected. Not about time, not about light, but about connection. Because hidden within the mathematics of space-time is a possibility so strange that it almost feels like a mistake. A structure that does not simply bend space, but links distant regions together. Not through the space between them, but by folding the structure itself. A bridge, what we now call a wormhole. But when Einstein first encountered this idea, it was not imagined as a gateway or a shortcut. It was something far more abstract. A way to avoid a deeper problem hidden in his own equations. The problem was singularities. Points where the mathematics of space-time breaks down, where density becomes infinite, where the known laws of physics no longer apply. These appeared in early solutions describing what we now call black holes. Regions so dense that nothing, not even light, could escape. Einstein was deeply uncomfortable with this idea. A theory, in his view, should not lead to infinities. It should remain smooth, continuous, complete. So together with Nathan Rosen, he explored whether these singularities could be replaced, not with endpoints, but with connections. And what they found was something remarkable. Instead of space-time ending at a singularity, it could be extended, stretched in a way that connected one region to another, two distant parts of the universe, or even two separate universes, linked by a narrow throat, a bridge between realities. From one side, it would look like a black hole, pulling everything inward. But instead of collapsing into a point, the geometry would open up, emerging somewhere else. A mirror image, a second region of space-time. At first glance, this sounds like a path, a passage, a way to travel instantly between distant locations. But the truth is quieter. and more limiting. The original Einstein-Rosen bridge is not traversable, cannot be crossed. The geometry itself prevents it. As soon as something attempts to move through the bridge, it collapses. The throat pinches shut faster than anything can pass. From the outside, it appears as if the object slows down, fading near the boundary, never quite making it through. From its own perspective, it is destroyed by the extreme conditions long before reaching the other side. The bridge exists, but only for a fleeting moment, a connection that is mathematically real, but physically unreachable. And this is where the deeper meaning begins to emerge, because the existence of such structures tells us something important about reality. Space is not simply a flat, continuous expanse. It has structure, topology. It can bend, stretch, and even connect in ways that are not obvious from local observation. Two regions that appear distant, separated by vast emptiness, may, in a deeper sense, be connected, not in a way we can easily access, but in a way that exists within the underlying geometry of spacetime. And this raises a quiet but powerful question. How connected is the universe? Really? Because if spacetime can form bridges, even if they are unstable, then the separation we perceive between distant points may not be as absolute as it seems. Distance, like time, may be more flexible than we imagine. Einstein himself did not pursue the idea as a method of travel. For him, it was a mathematical solution, a way to remove singularities and preserve the continuity of his theory. But later physicists began to explore the concept more deeply. Could such bridges be stabilized? Could they be held open? The answer, at least theoretically, is yes, but only under conditions that challenge everything we know about matter and energy. To keep a wormhole open, one would need something called exotic matter, a form of energy with properties unlike anything we encounter in everyday life. Matter that behaves in ways that seem almost impossible, pushing outward instead of pulling inward, violating conditions that all known forms of matter obey. There are hints of such effects in quantum physics, small, fleeting instances where energy behaves in unusual ways, but nothing on the scale required to stabilize a wormhole. And so, for now, these bridges remain theoretical, real in the equations, but not in experience. Yet even in their limitations, they offer something profound. They show that spacetime is not just a passive stage. It is something that can connect, fold, and restructure itself in ways that go beyond our intuition. And this connects back to the pattern we've been following. Reality is not fixed, not absolute, not as simple as it appears. Energy is discrete. Matter is uncertain. Time is relative. Space can expand. And now, it can connect. Each layer revealing a universe that is more flexible, more dynamic, and more mysterious than we once believed. And as we continue, another transformation awaits. Because space does not only connect, can also move. Not objects moving through space, but space itself, twisting, dragging, and swirling under the influence of massive rotating bodies. A subtle effect, almost imperceptible, yet deeply real. where even the fabric of reality begins to turn. Up until now, space has felt like a stage, a vast, silent backdrop where everything unfolds. Objects move through it, light travels across it, gravity bends it, but it still feels passive, something that exists but does not act. Einstein's deeper ideas suggest something far more subtle. Space does not just sit still, can move, not in the way objects move through it, but in the way it carries motion within itself. A kind of quiet twisting, a dragging of the very fabric of space-time caused not just by mass, but by rotation. This phenomenon is known as frame dragging. And to feel it, we need to imagine something unusual. Picture a massive object, a planet, a star, or something even more extreme, slowly spinning. In classical physics, this rotation would not affect the space around it in any fundamental way. The object spins, but space remains unchanged. In Einstein's universe, this is no longer true. When a massive object rotates, it does not simply spin within space. It drags space-time along with it, not violently, not in a way we could easily see, but subtly, persistently, like a slow current in a vast ocean. If you placed a perfectly free-floating object near this spinning mass, something that is not pushed, not pulled, not touched, it would still begin to shift. Its orientation would slowly change, not because of a force in the traditional sense, but because the very coordinates of space and time around it are being twisted. It is as if the grid of reality itself is turning, and anything within that grid must follow. This idea can feel abstract, but there is a quiet analogy that helps. Imagine placing a small leaf in still water. If the water remains still, the leaf floats without motion. But if the water begins to swirl, even gently, the leaf is carried along, not because it chooses to move, but because the medium itself is moving. Frame dragging suggests that space-time behaves in a similar way. Mass tells space how to curve, and rotation tells space how to twist. On Earth, this effect is extremely small. Our planet rotates, but its mass is not large enough to create a strong distortion. Detecting frame dragging here requires instruments of extraordinary precision, devices so sensitive that they can measure shifts smaller than the width of an atom. And yet, even here, the effect is real. Carefully designed experiments have confirmed it. Tiny changes in the orientation of gyroscopes, slight shifts in satellite orbits, all consistent with the idea that Earth's rotation is gently dragging space-time along with it. But in more extreme environments, the effect becomes far more dramatic. Near a rapidly spinning neutron star or a rotating black hole, space-time does not just twist gently. It swirls violently. In these regions, the dragging becomes so strong that nothing can remain still relative to the distant universe. Everything is forced to move along with the rotation. Even light, even the paths of particles, are caught in this twisting flow. Around a rotating black hole, there exists a region where standing still is impossible. Space itself is moving faster than anything could resist. Any object entering this region must co-rotate, carried along by the turning fabric of space-time. This is not motion through space. It is motion of space. And this distinction is important because it reveals something deeper about reality. Space is not empty. It is not a passive void. It is an active participant in the universe, capable of bending, stretching, expanding, and now twisting. And when we place this idea alongside everything we have explored so far, the pattern becomes even clearer. Energy is discrete. Matter is uncertain. Time is relative. Space can expand. Space can connect. And now, space can move. Each layer dissolves another piece of the simple, classical picture of reality. The universe is no longer a fixed stage with objects moving upon it. It is a dynamic system where the stage itself is alive, evolving, interacting with the things within it. And this leads to a quiet realization. When we move through space, we are not just traveling through a static environment. We are moving within something that can bend, stretch, and even carry us along in subtle ways we rarely notice. The paths we follow, the orbits of planets, the trajectories of light, are all shaped by this deeper structure. And yet, despite all of this motion, all of this complexity, the universe remains coherent, predictable, governed by laws that, once understood, reveal a kind of hidden harmony beneath the apparent strangeness. Einstein's hidden ideas do not break reality. They deepen it. They reveal that what we perceive is only a surface, a simplified version of something far more intricate. And as we move forward, we approach another transformation, one that shifts not space, not time, but matter itself, into a state where individuality begins to disappear, where particles lose their separate identities and merge into a single, unified existence, a state so strange that it feels almost impossible, and yet it exists. By this point, reality has already begun to feel different, not broken, not chaotic, but softer, less rigid than it first appeared. Energy arrives in packets. Matter exists in probabilities. Time shifts depending on motion. Space bends, stretches, connects, and even moves. But now, we arrive at something even more unexpected, a place where the very idea of individuality begins to dissolve. Imagine taking a group of atoms, tiny, distinct units of matter, each with its own position, its own motion, its own identity. In normal conditions, they behave independently. They collide, scatter, move randomly, like a crowd of people, each following their own path. This is how we understand matter. Separate, distinct, individual. But under extreme conditions, something remarkable happens. If you cool these atoms down, and not just to low temperatures, but to unimaginably low ones, just a fraction above absolute zero, their behavior begins to change. Their motion slows. Their individuality begins to fade. Their quantum nature, normally hidden beneath thermal chaos, starts to emerge. And then, at a certain threshold, they stop behaving like separate particles. They merge, not physically fusing, but becoming indistinguishable. Their individual identities blur into a single shared state. Instead of many particles, you now have one unified quantum entity spread across space. This is known as a Bose-Einstein condensate, and it reveals something deeply strange about reality. Because in this state, you can no longer point to one atom and say, this one is here and that one is there. They are no longer separate in the way we understand separation. They are part of a single wave, a single coherent structure. Matter becomes one. This is not just a curiosity. It is a direct consequence of the same principles we explored earlier. The wave nature of matter, the probabilistic foundation of reality. Under normal conditions, these effects are hidden, averaged out, smoothed over by the constant motion of particles. But when that motion is removed, when the system is brought into an almost perfectly still state, the deeper structure reveals itself. And what it reveals is unity, a kind of collective behavior where individuality disappears, replaced by coherence. All particles moving together, as if they are different expressions of the same underlying entity. This challenges something very fundamental, because we are used to thinking of reality as built from separate pieces. Atoms, particles, objects, each distinct, each independent. But here, at the edge of extreme conditions, that separation breaks down. It suggests that individuality may not be fundamental, that it may be something that emerges only under certain conditions, much like continuity or certainty or a shared sense of time. And this idea echoes something we have felt throughout this journey, that what we experience is not the deepest layer of reality. It is a surface, a stable, familiar layer built on top of something far more fluid, far more interconnected. In a Bose-Einstein condensate, we glimpse that deeper layer directly, a state where the boundaries between particles dissolve, where the system behaves as a single wave, a single presence. And this leads to a quiet, almost philosophical reflection. If matter can lose its individuality under the right conditions, if separate particles can become one, then what does that say about the nature of separation itself? Is the distinction between this and that truly fundamental? Or is it something that emerges only when conditions are right? Something that depends on temperature, on energy, on the environment? Einstein's role in this story is subtle but essential. He recognized the implications of Bose's work, extended it, and predicted that such a state could exist long before it was ever observed. Decades would pass before technology caught up, before scientists could cool atoms enough to bring this strange state into reality. But when they did, the prediction was confirmed, and with it, another layer of reality was revealed, one where matter is not always separate, one where unity is not just a concept, but a physical state. And as we take this idea forward, it begins to connect with everything else we've seen. Energy is discrete, yet can act collectively. Matter is uncertain, yet can merge into coherence. Time is relative, space is dynamic, and now, individuality itself becomes conditional. Each step dissolves another boundary. Each idea brings us closer to something deeper, a reality that is not built from isolated pieces, but from relationships, from connections, from structures that only appear separate from a certain perspective. And this leads us toward one final thread, Einstein's unfinished dream, a hope that beneath all these layers, beneath relativity, beneath quantum mechanics, beneath all the apparent complexity, there exists a single, unified description of everything, a theory that ties it all together, a hidden order beneath the surface. Whether that unity truly exists, or whether reality remains forever layered and incomplete, is something we are still trying to understand. And it is there, at that boundary between what we know and what we do not, that our journey begins to slow. By the time Einstein reached the later years of his life, he had already changed physics forever. He had reshaped our understanding of space, of time, of gravity. He had helped open the door to quantum theory. And yet, despite all of this, he believed something was still missing. Not a small detail, not a minor correction, something fundamental, because as powerful as his theories were, they described different parts of reality using completely different languages. On one side, there was general relativity, smooth, continuous, geometric, a universe where gravity is the curvature of space-time, elegant and deterministic. On the other side, there was quantum mechanics, fragmented, probabilistic, uncertain, a world where outcomes are not fixed until observed. Two descriptions of reality, both incredibly successful, yet deeply incompatible. And Einstein could not accept that this was the final picture. He believed there must be something deeper, a single framework, a unified field, where all forces, all particles, all interactions emerge from one coherent structure, not separate theories stitched together, but a single underlying truth from which everything else unfolds. This became his final pursuit, a search not for new phenomena, but for unity. He imagined a reality where gravity and electromagnetism, the two known fundamental forces of his time, were not separate at all, but different expressions of the same deeper field. A geometry so complete that particles themselves would emerge naturally from it, not as independent objects, but as features of the field itself. In this vision, there would be no need for randomness, no need for probabilities. Everything would follow from a deeper order, hidden but precise. It was a beautiful idea, but it was also incomplete, because while Einstein searched for unity in geometry, physics was moving in another direction. Quantum mechanics was expanding, growing, revealing new particles, new forces, new interactions. The world at the smallest scales was not behaving in a smooth, continuous way, but in discrete, probabilistic steps. And Einstein resisted this, not because he did not understand it, but because he believed it was not the full story. He suspected that beneath the randomness, there must be something more fundamental, something that restored order and determinism, a deeper layer of reality, still hidden. And so, for decades he worked, alone in many ways, exploring different mathematical approaches, extending his equations, searching for patterns that could unify everything into a single framework. But each attempt fell short. The equations became more complex, but the connection to observable reality remained unclear. Meanwhile, the rest of physics moved forward, embracing quantum theory, building what would become the standard model of particle physics. A framework that successfully describes 3 of the 4 known fundamental forces, but still leaves gravity separate. Even today, that separation remains. We still do not have a complete theory that unites gravity with quantum mechanics. We still lack the single framework Einstein dreamed of. His goal remains unfinished. And this is where his hidden idea becomes something more than a scientific pursuit. It becomes a reflection of something deeper, a desire to believe that beneath all the complexity, there is simplicity, that the universe, in all its strange behavior, all its uncertainty, all its relativity, ultimately arises from a single coherent structure, a unity that we have not yet fully seen. And when we place this idea alongside everything we've explored, it begins to resonate in a different way. Energy is discrete, yet follows precise rules. Matter is uncertain, yet forms stable structures. Time is relative, space is dynamic, and still everything fits together into a consistent whole. It is as if reality is both fragmented and unified at the same time. 2 perspectives coexisting, and perhaps that is the quiet truth Einstein was reaching toward. Not a return to a simple deterministic universe, but a deeper understanding where these apparent contradictions are resolved, where the probabilistic nature of quantum mechanics and the smooth geometry of relativity are not opposing descriptions, but parts of a larger whole. A reality that is richer than either framework alone. And yet, we are not there. Not yet. We stand at the edge of that understanding with theories that work, but do not fully connect. With equations that describe parts of reality, but not all of it together. Einstein's dream remains unfinished, but it continues to guide us, because the search for unity has not ended. It has simply evolved. And as we move forward, we will encounter one of the most profound challenges Einstein posed to quantum mechanics itself. A paradox that questioned whether reality is truly local, or whether distant parts of the universe might be connected in ways that defy everything we expect. A question that leads us even closer to the edge of what reality might truly be. By the 1930s, quantum mechanics had already proven itself. It could predict the behavior of atoms, explain the structure of matter, and describe light with extraordinary precision. Its equations worked almost perfectly, and yet, beneath that success, there was something deeply unsettling. Not a flaw in the calculations, but in the meaning behind them. Because quantum mechanics did not describe reality in the way physics had always done before. It did not tell you what is, told you what might be. It replaced certainty with probability. Instead of saying where a particle is, it described a range of possible locations, each with a certain likelihood. And for Einstein, this was not enough. He believed that reality must exist independently of observation, that objects should have definite properties, whether we measure them or not. The idea that something only becomes real when observed felt incomplete, as if part of the story was missing. So he proposed a challenge, a thought experiment designed to test whether quantum mechanics truly describes reality, or whether it is only a partial picture. This became known as the EPR paradox. Imagine two particles that interact in a special way, becoming linked, not physically attached, but connected through their shared history. After interacting, they move apart, drifting in opposite directions, separated by vast distances. According to quantum mechanics, these particles remain connected. In a very specific sense, if you measure one particle, you instantly know something about the other, not because a signal travels between them, but because their properties are correlated. They share a single description, even when far apart. This alone is strange, but the deeper implication is even more unsettling. Because if measuring one particle instantly determines the state of the other, no matter how far away it is, then something appears to be happening faster than light. An influence without a signal, a connection without a medium. Einstein famously referred to this as spooky action at a distance, and he did not like it, because it seemed to violate a fundamental principle, that nothing can travel faster than light, that influences must move through space, step by step, limited by the structure of space-time. But here, the connection appeared instantaneous, as if distance did not matter, as if space itself was not a barrier. Einstein's conclusion was not that the universe allows such strange connections, but that quantum mechanics must be incomplete, that there must be hidden variables, deeper properties that determine the outcomes in advance, restoring a sense of locality and realism. In other words, the particles are not influencing each other instantly. They were simply predetermined all along. But as experiments advanced, something remarkable happened. The predictions of quantum mechanics were tested again and again with increasing precision. And each time, the results aligned with the strange, non-local predictions, not with hidden variables, not with classical explanations, but with the idea that the particles remain fundamentally connected, even across distance. This phenomenon is now known as quantum entanglement, and it reveals something deeply unexpected about reality. Separation may not be absolute. Two objects, once connected, can remain linked in a way that does not fade with distance. Their properties are not independent, but part of a shared system, even when they are far apart. This does not allow faster-than-light communication. The structure of physics still preserves causality, but it does suggest that the underlying reality is not built from isolated pieces. Instead, it is woven together, a network of connections that exist beneath the surface, invisible but real. And this brings us back to something we encountered earlier, the idea of wormholes, bridges connecting distant regions of spacetime, and something even more speculative, yet deeply intriguing, the possibility that these quantum connections, these entangled pairs, may be related to microscopic versions of those bridges. Tiny, non-traversable links connecting particles across space. A suggestion that what appears separate is actually connected at a deeper level. This idea remains theoretical, still being explored, but it carries a quiet resonance with everything we've seen. Because once again, the boundaries we take for granted begin to dissolve. Distance may not fully separate. Time may not be universal. Matter may not be independent. And reality may not be made of isolated parts at all. Instead, it may be something more unified, more interconnected than we can easily perceive. Einstein introduced this paradox to challenge quantum mechanics, to show that something was missing, but in doing so, he revealed something else, a glimpse of a deeper structure, one that continues to shape how we understand the universe today. And as we approach the final moments of this journey, all of these ideas begin to come together. The discreteness of energy, the uncertainty of matter, the relativity of time, the flexibility of space, the unity of quantum states, the hidden connections across distance, each one a piece of a larger picture, a picture that suggests reality is not what it first appears to be, but something far more subtle, something layered, relational, and quietly mysterious. And now, we begin to bring these threads together. If we pause here, just for a moment, and look back at everything we've uncovered, a pattern begins to quietly reveal itself. Not a loud revelation, not a sudden answer, but a shape emerging slowly from the ideas we've been following. Light is not continuous. It arrives in indivisible packets. Matter is not fixed. It exists in a cloud of possibilities until observed. Time is not universal. It depends on motion, on perspective. Space is not passive. It bends, stretches, connects, and even moves. And now, we've seen that separation itself may not be absolute, that distant objects can remain deeply connected in ways that defy intuition. Each of these ideas on its own feels like an exception, a strange corner of physics, an unusual behavior that only appears under special conditions. But together, they begin to form something else, a new picture of reality, one where the familiar world we experience, the smooth, continuous, stable world, is not the foundation, but the result, an emergent layer built on top of something deeper, something more fluid, more relational, more interconnected. It is as if reality has two faces. The surface, where things are solid, time flows evenly, and objects are separate. And beneath that surface, a deeper layer where boundaries blur, where certainty dissolves, where connections extend beyond what we can see. And both are real, both are valid, but they are not the same. Einstein's hidden ideas begin to show us how these two layers relate to each other. The classical world, the one we navigate every day, is not wrong. It is a simplified version, a large-scale expression of deeper principles that become smoother, more stable, more predictable as systems grow larger and more complex. The randomness averages out, the probabilities settle, the connections become less visible, and what remains is the illusion of a fixed, continuous reality. But beneath that, the deeper structure remains unchanged. Energy still arrives in packets. Matter still exists as possibilities. Time still depends on perspective. Space still bends and moves. And connections still exist, even when we cannot see them. This realization does not break reality. It enriches it. It suggests that what we perceive is only part of the story, that the universe is not a simple, rigid system, but something layered, where different rules emerge at different scales. And this brings us back to Einstein's unfinished dream. The idea that all of these layers, all of these strange behaviors, might ultimately arise from a single unified structure, a deeper framework where quantum uncertainty and relativistic geometry are not separate descriptions, but different expressions of the same underlying reality. We do not have that framework yet, but we can feel its outline in the way these ideas connect, in the way they echo each other, in the way they all point toward a universe that is not built from isolated pieces, but from relationships, from interactions, from patterns that only become visible when we step back and look at the whole. And perhaps this is the quiet shift Einstein was guiding us toward. Not just new equations, but a new way of seeing. A way of understanding reality not as a collection of things, but as a network of connections. Not as a fixed stage, but as something dynamic, evolving, shaped by perspective, position, and interaction. And as this understanding settles in, something else begins to soften. The boundaries we rely on, between past and future, between here and there, between one thing and another, they remain useful, necessary, but no longer absolute. They become approximations, and in their place, a deeper continuity begins to appear. Not the smooth continuity we once imagined, but something more subtle. A continuity of relationships, a coherence beneath the apparent fragmentation. And this is where the journey begins to slow, because once you see this pattern, once you feel the shift from a fixed reality to a relational one, there is nothing left to chase, only something to sit with, to let unfold. And as we move into the final moments, we begin to let the ideas settle, not as questions to solve, but as a quiet awareness of just how deep the structure of reality might be. At the very edge of understanding, something changes, not in the universe itself, but in the way we relate to it. Up to this point, each idea has expanded our view. Light becoming particles, matter dissolving into probability, time losing its universality, space bending, stretching, connecting, and even moving, reality shifting from something fixed to something relational. But now, as all of these ideas settle together, they begin to do something quieter. They stop asking to be solved, and instead, they invite us to observe. Because when you follow these ideas far enough, you reach a place where explanation becomes less important than perspective, where the goal is no longer to force reality into something simple, but to recognize that its depth may not be reducible to a single, familiar picture. Einstein spent much of his life searching for that picture, a unified structure, a final clarity, a complete description where everything fits together without contradiction. And yet, even he reached a point where the answers remained just out of reach. Not because they do not exist, but because reality may not reveal itself all at once. Instead, it unfolds in layers, and we, as observers, move through those layers, understanding a little more each time, but never quite reaching the end. There is something calming in that realization, because it means the mystery is not a flaw. It is part of the structure. The same way the horizon always recedes as you move toward it, the deeper layers of reality remain just beyond complete understanding, not to frustrate us, but to invite continued exploration. And when we stop trying to resolve everything at once, something else becomes visible, the coherence, because despite all the strangeness, all the shifting perspectives, all the uncertainty, the universe remains consistent, stable, predictable in its own way. The laws hold, the relationships remain intact. Even when reality appears fragmented, it does not fall apart. Instead, it forms patterns that repeat across scales, patterns that connect the smallest particles to the largest structures, patterns that allow a universe governed by probability and relativity to still give rise to stars, galaxies, and the quiet experience of being here in this moment. And this is where the tone begins to soften, because the questions that once felt urgent begin to loosen. What is real? What is fundamental? What lies beneath everything? These questions remain, but they no longer demand immediate answers. They become something else, something you can sit with, like watching the night sky, not needing to understand every star, but simply feeling the depth of what is there. Einstein's hidden ideas lead us to this place, not to a final conclusion, but to an expanded awareness, a recognition that reality is richer than it first appears, that beneath the surface of everyday experience, there is a deeper structure quietly shaping everything, and that we are part of it, moving through space-time, experiencing one slice of reality, one perspective among many, feeling time as it flows, even though at a deeper level it may not flow at all, seeing separation, even though connections extend beyond what we can perceive, living within certainty built upon uncertainty. And none of this needs to be resolved, simply is. And as this awareness settles, the need to define everything begins to fade. In its place, something calmer emerges, a sense of being within a universe that is not fully known, but is deeply coherent, a universe that allows questions to exist without requiring immediate answers, a universe where understanding grows slowly, gently, over time. And in that space, the final piece of this journey begins to take shape, not as a new idea, but as a quiet reflection, a way of holding everything we've explored without tension, without urgency, just letting it be. And now, as everything begins to quiet, we arrive at the final shape of the journey, Not a conclusion, not a final answer, but a feeling, a sense of where all these ideas have been leading all along. Because when you step back from everything we've explored, something becomes clear. Reality is not what it first appears to be, but it is also not something chaotic or broken. It is something deeper, something layered, something that reveals itself slowly. Depending on how you look, light is both wave and particle. Matter is both definite and uncertain. Time both flows and does not. Space both separates and connects. And existence itself both divides and unifies. These are not contradictions. They are perspectives, different ways of touching the same underlying structure. And perhaps this is the quiet insight hidden within Einstein's work, not just in his equations, but in the way he approached the universe. That reality does not need to fit into a single, simple picture, can be richer than that, more subtle, more complete, precisely because it allows multiple layers to coexist. The world we experience, the one that feels solid, continuous, stable, is not false. It is simply one layer, a surface that emerges from deeper processes that are less intuitive, but no less real. And beneath that surface, the universe continues, quietly, unfolding through interactions, through relationships, through structures that connect everything in ways we are only beginning to understand. There is something calming in this, because it means that not knowing is not a failure. It is part of the experience. The universe is not something to be fully captured in a single explanation. It is something to be explored, gradually, patiently, and perhaps endlessly. Einstein spent his life searching for unity, for a single framework that would tie everything together. And while that final theory remains just beyond reach, the journey itself revealed something just as meaningful, that the universe is coherent, even when it is complex, that beneath uncertainty, there is structure, that beneath relativity, there is consistency, that beneath all the shifting perspectives, there is something that holds everything together, not in a rigid way, but in a quiet, flexible harmony. And as you sit with that, there is no need to resolve it, no need to simplify it. You can simply let it exist, the same way the universe does, layered, expansive, gently unfolding. And perhaps in that stillness, something else becomes noticeable. The present moment, not as a universal now, but as your now, your perspective, your path through this vast structure of space-time. A single thread moving quietly through something much larger. And that is enough. It has always been enough. Because even if reality is deeper than we can fully understand, we are still part of it, experiencing it, living within it. And that connection, however small it may feel, is real. So as the universe continues, expanding, shifting, revealing itself in subtle ways, you can let your thoughts slow. Let the questions rest. Let the patterns settle into the background. And simply drift within the quiet awareness that reality is not something you need to hold on to. It is something you are already inside, something vast and calm and endlessly unfolding. And with that, we gently come to rest,